matter abundance in SDSS galaxies. Okay. So, actually, I would like to remind you that there is a poster session in Slack. So please discuss posters already submitted, and also we would like to encourage people to submit posters. Even if you haven't registered for poster, it's okay. You can, if you have poster, please feel free to post it. Yeah.
Okay. Hi everyone. I'm Ling from Hsinchu, and my topic is environmental effects on the.
Please speak loudly.
Okay. The environmental effects on the evidence of dark matter in SDSS gases. So my talk will separate in several parts. First, I will talk about what is DNDGs and what is the importance of it. And I will talk about my method to investigate the environmental effects on DNDGs. Then I will show my preliminary results. So, what is DNDG? The DNDG is an aberration of dark matter diffusion gases, which the dark matter evidence is much lower than typical galaxy like our Milky Way. The typical galaxy, the ratio of dimensional mass to stellar mass ratio of typical galaxy is about 10, and DNDG is an order lower, about 2 or less. So we can consider the DNDG is a baryon domain galaxy. And here I list some currently 5 DNDGs here. And this figure is the first found DNDG NGC101052DF2, and which is also an ultra diffuse gas. And what is the importance of DNDG and why we need to find that? So in short, DNDG is an exception to our cosmology. The discovery of DNDG leads to a crucial problem. So that is, how do they form? In our popular cosmology lambda CDM model, a galaxy should be formed from a huge gravitational potential energy created by a dark matter halo in the center. But DNDG didn't have any dark matter, or very none of it have. So how can they grow or form a galaxy structure that hold for enough time to let us to observe it? The answer may be simple. It is the interaction between the galaxies. So a galaxy interaction could maybe form the DNDG by collision or tidal strip. Some simulation and theory suggest this kind of scenario, like the figure shows here. The two drop galaxy just collision, and the dark matter halo goes away and just left the dust and gas here. Then finally form a DNDG. So the behavior of DNDG can suggest us the nature of the dark matter or cold dark matter. So that is the importance of them. So here I will introduce the main idea in this study. That is, we want to constrain the characteristics of DNDGs. So now we don't know much about DNDG, but as I mentioned in previous slide, DNDG can form from a collision process. So it may be the more interaction between galaxies happen, then more DNTG can be found at here. So we assume the density of environment of a galaxy could affect on the dark matter evidence of the galaxy, such as DNTG. So when we talk about environment, we use the number density which is in N's nearest neighbor to estimate. So the N's nearest neighbor number density is divided as N divided by theta N squared, and theta N is the distance of the N nearest galaxies. So there's a sample for third nearest galaxy calculation. Our data is calculated selected by SDS DR12, and we combine the photometric spectroscopy and stellar mass table, and we drop the galaxy now in the main survey area that is comfortable to calculate the number density. Then we limit the galaxy to local universe and exclude the galaxy that are all of the first limit of SDSS. Then after number density calculation, we drop the non-elliptical galaxy. This is because the velocity dispersion estimation may be wrong for those galaxies. So we only keep elliptical galaxy by morphology using R19 R50 ratio and the gas catalog. Then we left 100,000 gases. In analysis, we calculate for 10th nearest number density, and we do a correction for this H gas again, and we normalize the density we calculate. The dark matter in galaxies is approximated by dynamical mass, which is simply calculated from the Wheeler theorem. So it's just like that. Then we select the DNTG, which we mean here is a galaxy with 2 sigma above the median of stellar and dynamical mass ratio. So it's a blue part of this figure. And we also curious about the opposite population, which is dark matter rich galaxy for comparison, which is the red part in the figure. And we separate the galaxy in different stellar mass range beams, and as you can see, in the top panel, the filtration function of dark matter diffuse galaxy DNTG is a little bit less on lower density region. So less is something out of our expect, and same thing happen in dark matter rich galaxies. And so we check the dark matter abundance of this galaxy as a lower panel. So in lower panel you can see the x-axis is the number density, and y-axis is the ratio of the dynamical mass to stellar mass. But you cannot see much information from this lower figure. So we are trying to find this relation for all the galaxies in our sample. So we check whole galaxy for the environment relation. So it's a surprising result that this medium environment is not depend on the dark matter abundance is independent from the environment, the density. We think this result is strange, so we check more. So for our first selection for galaxies, those less massive galaxies was not included because the 2 sigma selection is not quite good. So we make a stellar mass, dynamical mass cut to 10 to 10 and recalculate for first and second and third, fourth, and so on. We calculate those mass density, number density, and do the same analysis again to check if there's difference. The result shows no. The dark matter advance is independent from this density. Here comes the discussion in my summary. So in short, there is no dependence between dark matter advance and environment, which is number density in our study. That might suggest our assumption is wrong, but in other hand, it also suggests that number density might not be a good estimator to estimate the environment effect, because in such DNGG forming, the global potential could not affect the interaction between individual gases is more important. So we cannot use the number density to check this environment effect. And another possibility is SDSS didn't cover well for less massive gases. So for example, NGC 1052 DF2 has a stellar mass to 10 to 8, and this range is not covered good. We just have very few samples of them in SDSS, so we cannot check it. Then also we have a very rare possibility that CDM model could be wrong and we need to revise it. And I'm now working on to check the individual gas dynamics to form if there is a dependence to this local environment effect, then we could point out more information for dominant advance and DNDGs. So let's end on my talk. Thank you.
Thank you very much. There is one question from W. Okay. In your environment versus mass ratio plot, how could we understand the x-axis scale? So, yeah.
How do you?
Yeah.
I
So,
don't understand the scale.
This is a normalized number density. So it's normalized. The higher the density.
So what is the difference between the three plots?
This 3 part is different stellar mass range. I separate to want to check if there's difference between different stellar mass, but it's not. Okay.
Any other question? We still have 1 minute. Distant participants? Okay. Okay, if there is no question, yeah, let's thank the speaker again.